last time we started talking about the sun, and today we'll talk more about the sun and especially the things that we can see happening on the sun's surface, and we'll use our study of the sun to inform us about how other stars in our galaxy will behave. So this is going to be the easiest star to study, and we'll use that as an example for other stars that are farther away and therefore harder for us to study. So, and again, the sun is just very big compared to the size of the Earth. So the Earth is the little dot in the top right corner. So last time we talked about how the sun regulates its own core temperature. If the core gets too hot, it will increase the rate of its nuclear reactions. That makes the core expand in size. When something expands in size, it has more room for things to move around, and so it cools down. When it cools down, it shrinks and returns to the steady state. And then the reverse happens for if the core gets too cold, it will shrink. That shrinking will make things tighter together, making it easier for nuclear reactions to happen. Increasing nuclear reactions heats the core up, so it expands and returns to its steady state. So what were the main inputs and outputs for nuclear reactions happening in the sun? So what element or elements do you put in and what do you get out? So you put in hydrogen, 4 hydrogens, and you get out 1 helium. So as we learn about different types of stars, we will see how we start to fill in the periodic table. So hydrogen, our sun is turning hydrogen into helium, and then we'll see how other stars can turn other elements into heavier elements. So the photons that are generated in the core of the sun, we said last time, are gamma rays. So those are the highest energy photons. But on Earth, the photons we receive are typically in the visible wavelength range. So there has to be something happening in between the core and us. And those gamma rays are produced both from the byproduct of the nuclear reaction and from the matter-antimatter annihilations that happen as a byproduct of the nuclear reactions. So there's lots of gamma ray photons coming out of the core. So where those nuclear reactions are happening is in a state of plasma. So the 3 main states of matter are solid, liquid, and gas, and you can go between those different phases of matter by changing the temperature or pressure. There's another form of matter called a plasma, where if I increase the pressure and temperature enough, now what would have been a gas is now the electrons are no longer associated with the nucleus of that gas particle. And so that's what the definition of a plasma is. And so because the positive and negative charges are now separate, there's a lot of charged particles that a photon could interact with as it's trying to leave the core of the sun and head out to the outer layers of the sun. And so those interactions are governed by the electromagnetic force. And so photons are electromagnetic waves, and so if you have a bunch of electrically charged particles, then there's a lot of chance for interactions to happen. And so a photon that's generated in the core is not just going to freely pass all the way through the layers of the sun. It's going to take a lot of time to get out. The way that and so each time a photon, let's say, interacts with a proton or an electron, it's going to lose energy. And not only is it going to lose energy, but the direction that it's traveling is going to change. So we model that behavior in what's either called a random walk or a drunkard's walk. And so that's a real physics term that we use to describe basically a iteration of random motions over time. And so here's what a simulation of what that kind of motion looks like. So you could imagine the core is the center of this plot, and then the line that's being drawn is the semi-random motion of the photon as it's trying to leave the core of the sun and head out into space. So each time it's turning directions, it's interacted with a proton or an electron in the plasma and has changed direction and lost a little bit of energy. And so you can see it's not a straight path out from the center, and in some cases it's doubling back on itself, and so it can actually take a very long time for this photon to find its way out of the core and eventually leave the sun and head towards the Earth. So this is what that final path ended up looking like. And again, this is just a computer simulation of basically every few units it moves, it changes direction, and that's simulating it changing direction once a photon interacting with a proton or electron. And so here's some other just static images of what a simulation of that might look like. So you can see the blue, green, and red paths are all kind of probing different regions of the space, and they're all models of that photon bouncing off protons and electrons as it tries to leave the core of the star. So eventually it will make it out of the core and the radiation zone, and then it'll be more or less free to travel through the rest of the layers of the sun and out into space. But this process of the random walk takes anywhere from 10,000 to millions of years for that single photon to make it out of the sun. And so it's this process of all of these collisions that is resulting in the photons that reach the Earth not being all gamma rays, but instead being mostly, or the most common that we see are the visible wavelength photons. So the nuclear reactions are only generating gamma ray photons, and it's this process of all of these collisions that causes that photon to lose energy and then make it to the Earth as a visible wavelength photon. So the core and the radiative zone or radiation zone are where all of those collisions are happening. And then once the photon gets to the convection zone, it might bump into some things, but for the most part, it's just going to travel straight through the convection zone and out into space. That convection zone is responsible for basically what we see on the surface of the star. So when we look at the surface of the sun, it's not necessarily just a uniform sphere of light, but it's got this kind of granular texture on the surface, and that's because of these convection cycles. So where the hot gas is rising, you get the lighter material, and then that gas is going to cool as it gets to the surface and then fall back down, and those are the black edges of those kind of bubbles, basically. So the convection zone is responsible for the structure that we see on the surface of the sun. And so here's a simulation of what those convection cycles will look like, and so it's not always the same part of the surface of the sun that's hot or the same part that's cooler. It will not necessarily randomly, but it will kind of move across the surface over time. But how do we actually know what's happening inside of the sun, right? We can't send any probe close to the sun or it'll get burnt up. We can't cut the sun open and look at what's going inside. So we have a few techniques that we use to infer what's happening inside the sun. So first we can make models. We can study the vibrations that travel across the surface of the sun, and then we can observe the byproducts of what we hypothesize is going on inside of the sun. So those are the neutrinos. So this is a map of vibrations moving across the surface of the sun, and by studying these patterns we can tell what the material is made out of, what temperature it is, and use that to infer what's going on underneath of it. When we talked about the nuclear reactions that are happening inside of the sun, the proton-proton chain said we took 4 protons or 4 hydrogen nuclei, mashed them all together, and then some of the byproducts were these neutrinos. So a neutrino is a very small particle that does not have an electric charge, so it's not going to interact electromagnetically with anything, and so they're very hard to detect. So we've talked briefly about how we can detect those neutrinos. Here's another experiment that's set up. So this is Super Kamiokonda in Japan. So all of these little spheres on the ceiling of this chamber are the photon detectors, and then down below where these people are standing is a huge tank of water. So neutrinos don't really interact with anything, they just kind of pass right through. So they would pass right through all of this material on the roof and the detectors, and then if you have a large enough tank of water, you're basically just hoping that some of those neutrinos will accidentally bump into the water molecules, and when they bump into them, the water molecule will produce a photon, and then these detectors are looking for those photons. So these are so this is one of the experiments to detect neutrinos, and if there weren't nuclear reactions happening in the sun, then we wouldn't be detecting these neutrinos. So this is a picture of what the sky looks like in neutrinos. So basically we don't get any neutrinos from other places, and they're all coming from the sun. We've detected like a couple of other neutrinos from things that are not the sun, most notably a supernova in 1987, and that was really the first time we had detected light from a supernova and neutrinos from the same event. So really the sun just dominates all of the sky in terms of neutrino detections. Okay, so the energy from the fusion reactions in the core takes a really long time to get out of the sun, 10,000 to millions of years, and because it takes that long and there's a series of collisions, the photon has lost a bunch of energy and comes out visible wavelength light instead of gamma ray light. And we use mathematical models and observations of things like solar neutrinos to confirm our hypotheses about what the inside of the sun is like. So it takes longer for a photon to travel through the interior of the sun than it does to travel from the surface of the sun to the Earth. So this is true. So if you use the speed of light to calculate the amount of time it would take to travel from the surface of the sun to the Earth, it's very, very small compared to the tens of thousands to millions of years it takes for the photon to leave the sun. Okay, so now that we kind of understand what's happening inside of the sun, let's look at the surface and study what we can about the surface of the sun. So there's lots of activity going on the surface of the sun. So it's not just a smooth ball of gas and plasma, but it's actually quite violent at times. So there's a few different things that we'll talk about. These are kind of like weather on the surface of the sun. So there's sunspots, solar flares, and solar prominences. And it turns out that these events are related to the magnetic fields on the surface of the sun. So sunspots are these dark spots that you can see in the surface of the sun, and they are just a lower temperature than the surrounding material. And so this image is kind of an optical illusion in that this black part it's not like a void through the center of the sun, and it's still very, very hot. So remember, the surface of the sun is like 6,000 Kelvin. And so this dark spot is 4,000 Kelvin. So it's a lot cooler, but it's still way hotter than anything you're going to experience on the Earth. So this just appears dark because it's not as bright as the higher temperature stuff that's around it. So if you could remove everything else from the picture and just look at the dark spot, it wouldn't be dark anymore, it would appear light. It's just that the stuff around it is so much brighter that it makes it appear as a dark spot. And where the dark spots appear are related to magnetic field lines on the surface of the sun. One of the ways that we know that there are these strong magnetic fields is through something called the Zeeman effect. So we learned about spectroscopy, and we said that one line would correspond to one transition of an atom. So let's say we're talking about hydrogen, and we're going from the second orbital to the third orbital, or third orbital down to the second orbital, and there's a photon released. So that would, for example, correspond to one line. So what happens in the presence of a magnetic field is that one emission or absorption line will actually get split into different lines. So you have the central line, and then you have these two extra lines. So those extra lines are related to the spin of the electron, and that's related to some quantum mechanic effects. And that spin will align with the magnetic field. And so we can, by seeing this line splitting into three, we can infer that there's a very strong magnetic field in that region of the sun. So the Zeeman effect is one of the ways that we know that there are strong magnetic fields associated with sunspots. And so what we think is happening with sunspots are basically the start and end of where these magnetic field lines are breaking out of the surface of the sun. And as we'll see, we can kind of map these magnetic field lines by looking at these charged particles that travel along the field lines. So you get these very bright loops of gas that go from one sunspot to the other, and so these are basically mapping all of those magnetic field lines. And you don't see this very well in visible wavelength light, but you do see it very well in X-rays. So as these charged particles are spiraling around these magnetic field lines, they are releasing these X-ray photons. And so you have some magnetic field lines coming out from the surface of the sun at one sunspot and then terminating at another sunspot, and then charged particles from the surface of the sun are looping around these field lines, and you get these nice prominences coming off of the sun. The occurrence of sunspots on the surface is not constant, and so there's various levels of activity happening on the sun's surface at any given time. This is a graph of the number or the percentage of the sun's surface that's covered in sunspots at any given time, and you can see that it has some kind of cyclical pattern to it. And so this is about an 11-year period where you go from solar maximum to the next solar maximum, or solar minimum to the next solar minimum. So the top graph is the same. The bottom graph is plotting where the sunspots appear on the sun's surface. So at the start of a cycle, the sunspots will tend to appear kind of around 30 degrees away from the equator in the northern and southern hemisphere of the sun. And then as time goes on, they migrate or start to appear closer towards the equator of the sun. But either way, you still see about an 11-year period between the sunspot activity. And the bottom graph is sometimes called a butterfly graph because it's the dots look like they make the wings of a butterfly. So if you get some material that's coming off of the surface of the sun and then falling back down, those are called solar prominences. And so those magnetic field lines are allowing material to travel off of the surface of the sun. The corona, we remember, is the kind of outer layer of the sun's atmosphere. And if you look at it in X-rays, it's very bright, and that's because it's all of that material that's kind of coming off of the surface of the sun is getting trapped within the corona, and it's has a very high temperature, and so you get these X-ray emissions from that hot gas. So solar flares are photons that are released from the surface of the sun. These are X-rays. And then coronal mass ejections are basically mass that's getting leaving the surface of the sun and being put out into space. So the big difference between the solar flares, this is going to be photons, and then the coronal mass ejections are going to be matter. But through both of these types of events, you get material from the sun being released out into space. And so this material can travel very far, even towards the Earth, and we need things like a very strong magnetic field to prevent these charged particles from hitting the Earth. And so this is just a short video about the differences between the coronal mass ejections and the solar flares. And so some of those events can be highly energetic and very bad for the society that we've built. So we have a lot of telecommunication satellites that are orbiting the Earth that are all made out of electronics. So if you get an event like this that just so happens to be pointed at the Earth, it can fry all of the stuff we have out in space, and if it's very energetic, it might even fry a lot of electronics that we have on the ground. So monitoring the sun is something that's very important for knowing when an event like that could happen, or perhaps trying to mitigate some of the damage. So for example, you might be able to save some of your electronic equipment if you turn it off or shield it before that material gets to the Earth. And in the case of a coronal mass ejection, you might have a couple days warning to try to safeguard yourself. So the sun is basically responsible for all of the life on Earth, but it could be a little bit dangerous for the society that we've built. In addition to large events like coronal mass ejections, where material is escaping from the sun is also constantly releasing smaller charged particles into space, and we call this the solar wind. So these are the particles that are responsible for the pretty auroras that we see on Earth at the northern and southern poles when those charged particles interact with Earth's magnetic field. So these charged particles can be damaging, especially to electronics, and so they are a danger to satellites out in space. And so the solar wind, while it's capable of producing beauty in the auroras, it's also something that we need to be wary of. As we've seen before, the sun is rotating. But because the sun is not made out of a solid material, instead its outer layers are made out of gas, when it rotates, different regions of the sun will rotate at different speeds. So for example, material at the poles will rotate slower than the material at the equator. And so because there's these different rotation speeds, we get what is called differential rotation. The magnetic field lines at the surface of the sun are going to be affected by this differential rotation. As it spins, the magnetic field lines basically get dragged along with the rotation of the material of the sun. So this is kind of the picture of what you expect a magnetic field line to look like. So you get lines coming out of the North Pole, and then they circle around and terminate at the South Pole. But when your thing that generates the magnetic field is not solid, those magnetic field lines can get all twisted up, and where you get magnetic field lines crossing, we think that's where we can generate these sunspot pairs where we get a magnetic field line bulging out from the surface of the sun. So we've got a couple of videos that show what's actually happening on the sun, and then we're superimposing what we think the behavior of the magnetic field lines is to explain that behavior. So here's the magnetic field lines, and then they start to basically wrap around themselves as the sun is rotating, and then you get, basically it goes haywire from a nice, well-behaved system. And so here's a couple of longer
These are images of the sun.
simulations.
These are images of the sun in visible light from NASA's Orbiting Solar Dynamics Observatory, or SDO. At visible wavelengths, the sun is relatively featureless, its surface marked only with occasional sunspots carried into view by the sun's rotation. These sunspots can change shape in hours or stay stable for days. Ultraviolet light on the sun is created by energetic ions guided by magnetic fields, so these magnetic fields form glowing lines in ultraviolet images from SDO. The magnetic fields are more intense near sunspots, forming loops of plasma called coronal loops, which change and grow in seconds. In ultraviolet light, the sun appears very active. Using images from SDO in different wavelengths and polarizations, maps of the magnetic field at the sun's surface can be created. In these magnetograms, white and black indicate strong magnetic fields pointing out of and into the sun, while gray indicates weak magnetic fields. Coronal loops form between regions of intense opposite magnetic fields. From these magnetograms, we can create models of the solar magnetic field above the surface of the sun. This particular model is called the Potential Field Source Surface Model, or PFSS. The sun's rotation has been stopped so that the magnetic field lines are easier to see. Many of these lines curve and connect back to the solar surface on both ends. We call these field lines closed and color them white. The highest concentration of such lines is in regions of intense magnetic field. These are called active regions, and the closed lines in these regions closely match the coronal loops visible in ultraviolet light. Other field lines emerge from the surface and head off into space. We call these field lines open and color them green if they emerge from a positive magnetic field region, or violet if they emerge from a negative field region. These open field lines often correspond to regions called coronal holes, which provide a fast track for charged particles to leave the sun and become part of the solar wind. Magnetic fields are everywhere in space, but we can only draw some of the lines that show the shape of the field near the sun. As the magnetogram on the surface changes, so do the shapes of the lines. You may notice jumps in the field lines as they change in time. This visualization shows 4 years of the sun's magnetic field. The magnetic field extends outward to cover the entire solar system and beyond, interacting with all of the planets. By studying the magnetic field at the Sun's surface, we are gaining insight into the nature of the vast region dominated by our Sun.
And then one more simulation. So for this one, I want you to see how when we're talking about the north and south pole of the Sun, it's not a static location, and you can see it's kind of moving around fairly often. And so the north and south pole of the Sun can actually flip orientation every so often. And we also think that this happens on the Earth, and we think that we are potentially heading into a period of time where the Earth's magnetic field lines might be flipping. So the north pole of the current magnetic north pole of the Earth might switch and become pointed at the south pole, and then it doesn't necessarily mean much in terms of life on Earth, but it might mess with some like calibrations for how we have set up our electronics and stuff. So a lot of people who are skeptical about climate change will try to use the sun's activity to explain temperature variations on the Earth. And so there is a solar cycle, and so you might be getting a little more energy on the Earth from the sun at some times than at other times, and that's plotted in the blue line at the bottom. But you can see there's not very much correlation between that blue line and the red line, which is the average temperature on the Earth. So if anything, we should be heading into around 2015, we should have been heading into a period of solar minimum, but you can see the temperature on the surface of the Earth is just continuing to grow. So you're not going to get out of climate change by saying that it's the sun's fault and therefore I don't have to do anything about it. So the humans are really what is responsible for climate change, and we need to do something about that. So we think the main causes for all of that activity we see on the surface of the sun are due to these magnetic field lines. And because the sun is a not solid object that rotates, it has what's called differential rotation. So the material at the poles will rotate at different speeds compared to the material at the equator. And so that causes your magnetic field lines to get all twisted up, and that can lead to sunspots, and then solar prominences, coronal mass ejections, solar flares, and those events can cause problems for all of the electrical society that we've built on Earth. And the sun's activity follows this about 11-year period for going from solar maximum to the next solar maximum. And you'll, in the lab, starting on Wednesday, we'll do some work with the sun's activity and sunspots.